in the unified protection systems, in virtual memory, there is usually a read-write permissions on certain pages of blocks. Well, file systems also have these read-write execute bits for protection of files. So can we just like merge them together? So, file systems. So some of the core components of file systems is it provides a high-level abstraction to disk. It gives a quick access to metadata. It handles some management with file names and directories. It handles space with of your storage device, and it gives you some protection and some integrity of your files. So that's pretty cool. Good. So if you were to input NVRAM, and NVRAM is byte addressable, so how would the performance of having an NVRAM system compared to a block I/O system? So how would you manage inodes? Because what if you make your block size really small? You need a lot of inodes, and that would be kind of difficult to manage. And how would you handle space if both your files and programs and the stored state of your programs and the execution state of your programs are all in the same system? How do you manage that? And as I said before, do we need that block buffer layer as before? Do we need page caching? Just kind of repeating myself right there. So I got this diagram from Dr. Schu's slides. Kind of sorry for like stealing pictures. But anyways, well, there's a couple of states of what programs can be in. There could be a package state before you even get the file, a post-installed state, so when you install it, an execution state. And this has a code segment, stack, heap, and with our current system, we need a loader, and if we have an NVRAM system, how are faults going to be handled? So if you have an error in your code, it's going to persist. And how would you do some updates to the program if your program is already in memory and it's technically running against the memory? How do you update that if it's being referenced? So those are some of the questions that it's raised. Like I said before, data corruption, code corruption. Do we even need a loader? How do you stop an app? What does it mean to stop an app? What does it mean to launch, update, or reset an app? So when you're booting an operating system, you see these windows right here. So NVRAM, can NVRAM be portable? That question right there raises that in our current system, when it's turned off, you can take out as many RAM sticks as you want from your computer system. So if I turn off that computer right now, I can just take out some RAM sticks, and it'd be cool. I can take out a hard drive if it's not the OS or the boot partition, or the hard disk that has the boot partition in it. I can just take that out and it will be okay. But if we have NVRAM, how is that going to work? So do you get what I'm saying right there? Okay. So OS initialization is pretty much what the boot thing means. Software rejuvenation. So if you turn on your computer, how does it know which programs were supposed to stay on or not? And one cool idea that I saw in a UW paper was, what if you have your system, your CPU just be turned off, and your NVRAM, your I/O, and DMA controller be on and be communicating each other. So if you have your cell phone, you can just have your DMA controller be connected to your cell phone antenna, and if it gets like a phone call or detects a phone call, it sends an interrupt to the CPU and turns it on, and you're right back into execution state because everything's in NVRAM or your memory system, so you can execute right away. Oh, that's what that says. That was a lot. Okay. NVRAM OS research. This is just I just found a bunch of papers and YouTube videos and some PowerPoint slides from NVRAM OS conference website, and just kind of took those and put some of them in here, the ones I thought was interesting. Whew. Okay, we have 10 minutes. So the first one is kind of simple. Current systems, they have a log file and a buffer cache for backwards compatibility. This journaling area shows what are the commits that's supposed to be committed to the hard drive, and when you reboot, if there's a crash that has happened in your program, this journal area is able to know where to rewind your writes back into your storage, so your storage and RAM are in consistent state. So their idea was that why not just put the buffer cache and journal area in just in NVRAM and just put them together and use the same buffer, and just by doing that you reduce the amount of secondary storage writes and the memory interaction. So here's an example. We update these words. Pretty much, this right here shows an example of what would happen if we crashed right after the updates, but before we start committing our updates to secondary storage. Your memory would be inconsistent, but your secondary storage would be consistent, and that's the important part. Well, what if we crash after the checkpoint? Well, they suggest we put some locks onto these, on each byte, so we know which commits are actually the one that's supposed to be in the transaction. So we're in the middle of committing W and E to secondary storage. Well, it crashes before E finishes. But because we have these locks, we know these are not valid. So we can just rewind and do these commits again, and we should be consistent.